52, we were talking about rate laws, and we learned that there are the three different kinds: the first order, the second order, and the zeroth order. And those are determined by the exponents on the reactants. Well, now we're going to actually have what's called an integrated rate law, where it kind of changes and makes a new equation to help us see things linear in a linear fashion. So for first order, we know that this happens when the power is 1. And this type of reaction says that if the concentration of the reactant doubles suddenly, then the rate of the production will also double based on that rule. Okay, so this is our integrated first order rate law equation. It's set in a linear form, y equals mx plus b. So in that fashion, y is equal to the natural log of the concentration of A. X is time. The slope, m, is the negative of the rate constant. And the y-intercept b is the natural log of A0, which that means the concentration at the initial time of 0 seconds or minutes or whatever. So it's the initial concentration before it gets started. So if we were to plot this, we would have to see that when we take the natural log of the concentration of A versus time, and it would be a straight line, that would prove that it is in fact first order. Okay? The ratio of the two concentrations can also be shown in that bottom equation. So we are going to actually use Google Sheets to graph equations and graph data to see that what order it is. Okay? So for example 2, we're going to verify that it's first order by graphing correctly and then calculating the rate constant value, because when we know it's linear, then we can figure out the change in y of the change of x to find the slope. Okay? So going over to Google Slides, I typed in the information from the table. We want time to be the x-axis, so I typed that first, and then I have the concentrations given in the table. Well, we need to graph the natural log of the concentrations in order for it to be linear. So to do that, you go into the first box, and you need to start the function, so you hit the equal sign. And then we're doing natural log, so if you type in ln, then the ln function, the logarithm, should pop up. When you click that, then it lets you put in a value. Well, you could just highlight the box that's next door and then hit enter, and it will take the natural log for you. Instead of typing all of that in again for all those problems, when you highlight that first box and there's that little square, just drag that down to include all of the rows you want to find the natural log of, and it will do it nice and quickly for you. When you are graphing, make sure that you highlight column A first, and then hit control and you can highlight column C, and then you go into insert chart, so that's how you insert the chart, and then go to chart types, click on line, we want a line graph here, and then because we want to see it's linear, and then say using column A as labels. Okay, then we need to add a little bit more information so that we know what's going on here. So the chart title, we took time versus the natural log of the concentration of N205, just for a nice title. I don't really need a legend because it's just one line. And then I'm going to go down for the axes to label those. The horizontal axis is the time in seconds, and then the left vertical axis is the natural log of the concentration of N205. Alright, so then that gives us a nice indicator of what we got. So then I'm going to go ahead and insert that in, and I hope that you can see that. Okay? Alright, so we have our graph, and that is what we wanted to do, is verify that it's first order because it's linear. Now we need to calculate the value of the rate constant, where the rate is equal to the change in y over the change in x, or the change in the ln concentration versus time. So to do that, I'm just going to go ahead and write on here. So we know that the slope is equal to the negative k. So let's find slope. Okay. And it doesn't matter, it's just change in y over change in x. So I'm going to pick, to make it easy on myself, let's do the last two rows. Why not? So the ln value is negative 5.075-ish minus a negative 4.382 over the times 400 minus 300. So when we solve that out for the slope, I got negative 0.00693. And that's going to be per seconds. or just the way that things work out. Okay, well we know the slope is equal to the negative of k, and we just solved for the slope. So I just need to change the value, and that's the value for k. So k is equal to, and I'm going to put this in scientific notation, 6.93 times 10 to the negative third per second. All right, not too bad. You could, if you wanted to, figure this out on the computer as well. But I just decided to do it in person. All right, so then using that information, we're now going to do example 3, where we need to calculate the concentration of the N2O5 at a specific time. Okay, well, we're actually going to just go back to the integrated rate law, which is the natural log of the concentration, N2O5, is equal to the negative k times time plus the natural log of the initial concentration. Okay, well, I know I can plug some stuff in. All right, I don't know anything about the concentration. That's what I'm solving for. I'm going to have to keep that for now, exactly how it is. I just solved for the k value, 6.93 times 10 to the negative third. I'm going to take that times my time that I have, which is 150 seconds from the problem, plus the natural log of the initial concentration. Well, if you look back in example 2 at the table, when time equals 0, that's the initial concentration. So that would be 0.1, and they have a couple zeros for sig figs after. Okay, well, solving it out, the natural log of the N2O5 is equal to, and then multiplying those two together, I got negative 1.0395 minus, and then the natural log was, we could actually take that from our Google sheet if you wanted to, that. So again, getting it more simplified, is equal to negative 3.3425. Well, now we need to get rid of the natural log because I want to just know the concentration. And the inverse of the natural log is the e to the x function. So I'm going to take the e to the x to that side, so that goes away. And then I just have to take e to that power. And so then that tells us that the concentration of the N2O5 is going to be 0.035. And it's moles per liters in the table for the concentration, or you can put molar. Either one works. Okay? So that's another way to use their integrated rate law. Well, when we have our order reactions, we also have what are called half-life reactions or equations. So the half-life is the time required for a reactant to reach half of its original concentration. Okay? So we symbolize that by T to the 1/2. So for our first order reaction, this is the equation for the half-life of a first order equation. It's found in your textbook if you really want to see the derivative of it. But note that for a first order reaction, the half-life does not depend on the concentration. So we just have to know the rate, or the rate constant, and plug that in. Okay? So let's use that equation for example 4. For a certain first order reaction, it has a half-life of 20 minutes. So we need to calculate the rate constant. Well, if I know that my half-life is equal to 0.693 over k, I can plug in 20 minutes and find what k is for the first part. So I'm going to plug in my 20 minutes is equal to 0.693 over k. So you can think about that as cross multiplying if you want to. But k, I get to be 0.03465. And then I'm going to put a unit of per minute because the time was in minutes. Okay, so that's one of our answers. And then we want to know how much time is required for the reaction to be 75% complete. So this is where we're actually going to use the equation that we saw before, the example 2, where we take the natural log of the initial concentration over the concentration at a given time is equal to k times that time. Okay? Because we want to solve for k. Well, this 75% complete thing, okay, if we think about it as percent yield, we would say that if it's 75% complete, then that means that there's 25% of the original left. Okay? So then when we know that that's how much of the original is left, then the concentration from, like, it's like a percentage, right? So then the concentration of the A that's left over the initial, what it started with, is equal to that 0.25 in decimal form instead of percentage form. Okay, well then, if you notice, this is flip-flopped from what's in that equation. So we're going to take the inverse of this in that equation to solve for t, where we have the natural log of 1 over 0.25 is equal to our rate constant we just solved for, 0.03465, times our time, which is what we're trying to solve for, times t. Okay, well when I took the natural log of that, I got 1.386 is equal to our rate constant times time. So the time is going to be, when you solve that out, 40, and with sig figs, I'm going to go 40.0. And we're going to use minutes because our half-life was given to us in minutes. So that's just another manipulation of using our equations, okay? So we just have to make sure we figure that out correctly. So now let's talk about second order, okay? We have another integrated rate law for the second order equation, where this time it's talking about the inverses, okay? So second order means it has a second power of 2, right? So with the inverses here, that tells us that when we graph the inverse of the concentration of A versus time, then that produces a straight line to tell us that it is in fact second order, okay? And then we also have a half-life equation for this as well, where notice it's 1 over the rate constant times the initial concentration. And this derivative, how they derive this is found in your textbook, if you would like to know. So, for example 5, we have butadiene reacts with its form and its dimer according to the equation shown. Using this equation, is it first or second order? What's the value of the rate constant, and what's the half-life? Okay, using this information. So let's go back to our Google Sheets and figure it out. Okay, well we need to know if it's going to be first or second order. So we're going to have to graph the natural log like we did in example 2 to see if it's straight or of a linear equation. Or we're also going to compare that to the inverse to see if that is in fact the linear equation. Okay, so just setting it up in here to make my life easier. Remember, when you're in the box, you hit the ln and then, or the equal sign, then ln for natural log, highlight your box and hit enter. And then highlight it again and drag down so you don't have to type that so many times. It's just a wonderful thing about doing this in a spreadsheet. And then for the other one, the inverse, all you have to do is hit equal sign and then 1 divided by, and go back and click your B column, okay? And hit enter. And then drag down to fill it in. And all that math is done for you. So now let's graph, okay? We're graphing time as the x-axis, so make sure you highlight that first. Okay, so I got my time highlighted, and then control, I'm going to do the ln next. So once those are highlighted, then I can go insert chart, and I want to make sure it's a line, and I want to use column A as labels, and so there we go, I got my chart. That doesn't look very linear. But anyway, let's just label a couple things so we don't get confused later. So the chart title is going to be time versus the natural log of the concentration. I'm just going to put C to save time. And then for the axes, the x-axis is the time in, it was given to us here in seconds. And then the left vertical, I'm going to call that the natural log of C to save time. Okay, I'm going to go ahead and insert that graph. So that's not linear. So I hope the next one is. So again, let's go back. Let's highlight time, control, highlight the inverse column, not including the top, otherwise you get messed up and it doesn't work right. Then go insert chart, pick line, use column A as labels. Hey look, that looks pretty linear to me. More linear than the last one at least. So this time is time versus the inverse of C, so 1 divided by the concentration of C. And then labeling my axes. If you don't label the axes in the quiz, I'm going to take points off, so you're going to have to do that. Left vertical is 1 over the concentration of C. Alright, so looking at our two graphs now, I'm just going to cover up my data for a really brief second. The linear is the inverse. So that tells us that since the linear is the inverse, then that means that it's going to be a second order reaction. Okay? So then now for the rest of the information, we know to solve for it by knowing that it's a second order equation. Okay? So now let's figure out our slope. Okay, we know from our equation that the slope is going to be the positive value from the equation that I showed you before. So K is equal to our slope, and it's a positive K. So whatever the slope is, that's going to be our K value. So I'm going to just cover up that one that doesn't matter anymore so that I can find my K. Okay, so the slope, or K, I'm going to pick which two lines? Let's just pick the first lines. Why not? First and, oh, I picked first and last, so let's do that. Okay, so y over x, right? So I'm going to take 480.77 minus 100 over 6,200 minus 0. That makes life solving a little bit easier. And when you solve that out, I got to be 0.0614. So that is my value for K, because that's the volume, the slope, and the slope is equal to positive K from the equation. And now we have to figure out the half-life back from the other one. So now that we know K, to find the half-life equation is up above there on the page, and the half-life is equal to 1 over K times the initial value of A, concentration of A. So 1 over my K I just solved for, which is 0.0614, times my initial value for the concentration of A, which is right here, 0.01. So when I solve out that, the half-life is 1,630 seconds. Alright, so more manipulation showing you how the second order works. Last order is the 0th order. Most reactions involving a single reactant show either first or second Cornetics, but however, sometimes there can be a reaction where it has a 0th order reaction. So here's our integrated rate law, where the y is just the concentration of A, the slope is negative K again, x is T, and the initial concentration is the y-intercept. So there's no inverse here, there's no natural law. So that means when we graph time versus the concentration, and that's linear, then that would give us the indication that it is 0 order. Alright? For the half-life of this equation, it's the initial concentration over 2 times the rate. 2 times the constant. Okay? 0th order reactions are most often encountered when a substance, such as a metal surface, or an enzyme is required for the reaction to occur. So this doesn't always happen naturally. Okay? We're not going to do an equation or example of this because we've done a lot of examples, but we need to know, just for future reference, that when you have more than one reactant, the integrated rate law can be treated by choosing conditions in which the concentrations of only one reactant varies in a given experiment. So this is done by having the concentration of one reactant remain small compared to the concentrations of all the others. So that would give us the rate law indicated. That reduces down to the rate law times the rate constant times the concentration of the one that's most important. Okay, so the K with the apostrophe is like a different kind of rate law. So then, last but not least, this table is in your notes. It's probably hard to see right now, but this is just a summary of all your equations. You're going to have to know this stuff when you take the quiz and when you take the test. I might give it to you if I'm nice. So, good luck. Let me know if you have questions.